Hi. In the last video I worked on getting the ALU Adder integrated into the CPU build. And I had some good parts to that. We discovered a few things and worked through them, and there were a few issues that came up as well. In the end, I realized I had painted myself into a corner and had a pretty severe timing issue that needs to be sorted out, and that's where we left that video. I've been concerned about the timing of the ALU for some time, wondering if things were going to work out the way that I wanted them to. And they're not. And so my concerns have actually come to pass, and the struggle is real. Anyway, it's time to drop back tin and punt and figure out what we need to do to make the timing correct on the CPU build and see if we can add two numbers together. Once again, I've set my goal on that this video, and hopefully we can get there. Well, enough of the cliches, let's get right into this. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. I want to spend a good few minutes and try to define the problem here. Now, I'm going to use some graphics for illustration, and hopefully this will be a little bit less boring than just a PowerPoint presentation. I think it's important to understand where I'm at here with this and how I got to this point and what some of the solutions are to get myself out of this. So bear with me as I go through this. I hope you can stick with me. All right, for the ALU adder, there are 5 signals that need to be coordinated and worked out timing-wise. At least that's where we started at the beginning of last video. Those 5 signals are the assert out onto ALU A, the assert out onto ALU B, the assert of the adder results out onto the main bus, the target register load signal, and the end latch signal. Now, ALU A, or the left-hand side of the operation, and ALU B, or the right-hand side of the operation, were both intended to be asserted out onto their respective buses during the entire clock cycle. So this is the high level, the falling edge, the low level, and the rising edge at the end of the clock cycle. Similarly, the ALU adder result was supposed to be asserted out onto the bus during the entire clock cycle as well. Now, all 3 of these are active low signals, and so the signals themselves drop at the beginning of the clock cycle and remain low for the entire clock cycle and return back high at the end. So something else can take over that particular bus and do whatever it needs to do. Now, the load signal is a little bit different. It uses the spiked clock, as I call it, to create a short signal that occurs shortly after the rising edge of the clock. And it's intended to have a short-lived high cycle and then return back low for the rest of the duration of the clock. Now, this is inverted. It uses the HC 138s in order to demultiplex that signal at the register. And so it's typically a high signal which goes low and then returns high. The load signal itself is an active low signal. And since it's an active low signal, if anything happens to change while that signal is low, the register itself will update its contents. It does not have a single event latch that takes place. Now, this is on the counter ICs. This isn't the latch register IC. The final signal here is the end latch signal. Now, that's simply the inverted clock, such that halfway through the clock cycle on the falling edge of the clock itself, now the intent of latching on the falling edge is to allow memory to sort itself out so that the contents of memory are available on the next clock cycle. Now, that all should work great in theory. But in the last video, I observed some concerns with the contents of the ALU adder changing partway through as the latches were taking place. And rather than research the root cause of that, what I opted to do was to insert an ALU inputs latch so that I could latch the input into the ALU, and that would then therefore keep the output stable throughout the rest of the clock cycle and persist that value into future clock cycles if nothing else was using the ALU adder. Well, I think you can see the problem. It boils down to timing. If the inputs are latched at the exact same time as the register is loaded, and that is committed with the rising edge of that load signal, then there's no time for the ALU to actually compute its output, and it's going to latch the previous result, which is what I'm observing. At this point, you're probably saying, that's great, Adam. How are you going to fix it? But what I am thinking is I'm going to replace two of these signals. I'm going to replace the ALU input latch with an ALU output latch. And the latches are tri-state, so I'm going to use that as also my line driver. And I'm also going to replace the ALU output assert with a different shaped signal so that it is only asserting out onto the main bus when the ALU output is actually valid. In other words, after that latch has actually taken place. So now, once again, I am concerned about timing. The ALU adder output latch will happen on the rising edge of that spiked clock. The result register will be committed on the rising edge of that signal, which happens to be the falling edge of that spiked clock. And I'm hoping that there's enough latency in between those two to allow that to actually take place. I'm not certain at this point. We'll have to see if we can fine-tune that, and I may have to lengthen the width of that spiked clock. That then will end up shortening or reducing the frequency at which I can run this CPU as well. We'll have to see how that works out. It is important to understand that the ALU output latch and the assert out onto the main bus are going to happen at relatively the same time within an inverter of each other. And that is to make sure that those signals are congruent. Okay, well, that's enough of me rambling on about this. Let me get the build out and we'll start making changes and see if we can't get this thing to add a couple of numbers together. Okay, the first order of business is down here in the corner. I need to undo the changes I made, so I no longer need the line drivers here. I no longer need the latches here. These orange connections can come back down here to where they were originally and be wrapped around the bus lines here that are ribbon cables. And then I want to swap out these resistors, these pull down resistors, for 10K ohm resistors. Get that process started as well. So let me jump in on that and get a lot of that work done quickly so we can get it out of the way and then start focusing on signals. Well, I promise to always show you the good, the bad, and the ugly, but I don't see a need for you to have to watch me correct my mistakes. So I'm going to jump through this real quick and get back to the real meat of what we're trying to accomplish here. And I just need a minute to clean up my mess here, and then we'll come back to latching the output. Okay, while I was editing the last segment, I figured I'd better try this and make sure I didn't introduce a problem. And I introduced a problem. So I've been probing all over everything here, trying to figure out exactly what's been going on. And one of the things I noticed is that the inputs A on the least significant bit, the least significant bit coming off of ALU A, the least significant bit of the adder is up here and they're tied high and low. But it's 1.5 volts coming out of the input pin. And if I look here at the 10,000 ohm resistor, I've got a voltage drop over that of 1.44 volts. The resistor is not overcoming or pulling that signal low. But now if I unplug this, now look what happens. So I no longer have ALU-A attached to the adder, and all of a sudden my voltage comes down, or my voltage comes up. So I'm not exactly sure what's going on here, but I definitely have something going on. Now, to make matters even more interesting, I have LS line drivers here for ALU-B input, and if I check my B input over here, I legitimately have a low input, 0.12 volts. And again, if I disconnect ALU-A from the adder completely, I come out of reset. So there's something going on here with this adder circuit that is really perplexing me. Now, I don't have the background and education to be able to go through and read these things and understand them before I start assembling circuitry. So I'm learning as I go here, and it's trial by fire. But I saw something here in the data sheet for the 74LS83 ICs, and that is this input clamp voltage here. 1.5 volts. Now that's a negative 1.5 volts. I assume that that is voltage coming out of an input pin, and it happens to correspond to about what I'm looking at. Now my input current for my low level is minus 0.8 milliamps. Now if I do the math on that, 1.5 divided by 0.0008, 0.8 milliamps. I need something smaller than an 1800 on 1900 2000 ohm resistor to overcome that. Is that what I'm reading? Certainly a 10,000 ohm resistor isn't overcoming that. Well, let me show you what I built. Well, it's rare when I get to zoom down like this anymore. So this is a single 74LS83 IC. This is the 4-bit adder I've used in the build for now. And what I've done is I've just tied things up similar to what I have in the ALU Adder, with the outputs coming over here to the LEDs tied by 1K resistors to ground so that I can see the output. This would be power, and when I power this up with all of my inputs, including my carry flag, tied low through 10,000 ohm resistors, my expectation is that all of these are going to remain off, and they do not. All right, so these are 10,000 ohm resistors. If I was to take one of the lower inputs and replace a 10,000 ohm resistor with a 1,000 ohm resistor, I happen to catch the second bit here. It's able to pull it low. All right, I have a 1.5K ohm resistor that's available to me. It's able to pull it low. I have a 2K ohm resistor. It's able to pull it low. A 2.2K ohm resistor. It's able to pull it low. Now this is a 2.7K ohm resistor. It's still able to pull it low, but when I get to a 3.3K ohm resistor, it is no longer able to pull that low. Certainly a 10,000K ohm resistor is not able to pull that low. This was an interesting finding, an interesting understanding. Now, the 2.7 to 3.3K, I can certainly grab a, let's see here, where is it? A 2K. And then a 1K. So I have a combined resistance of 3K. And the 3K is not pulling that low. So between 2.7K and 3K, there's somewhere the magic number that's able to overcome that 5 volts, which I found to be very interesting. My plan has always been to use the 74HC283 in the actual PCB build, but I was curious about this clamp voltage, and the 74LS283 has a line about the same input clamp voltage of negative 1.5 volts. But now if I look at the 74HC283, I don't see anything in here about a clamp voltage, and I believe that's related to the TTL logic versus the CMOS or MOS logic, metal oxide semiconductor. Oh, but I've got those terms right. Anyway, I don't see anything about a clamp voltage here, so I don't believe I'm going to have a problem with this in the final build, and I think that's a good thing. But that said, however I solve this problem here has to be compatible with how I would solve it using the HC logic. Adam, you're going to ask, how are you going to solve that? Well, I do have a plan. Let me show you. Now, in all of this, I did notice that the ALU inputs for B worked, whereas the ALU inputs for A did not. What's the difference? The difference is there is a line driver that is sitting in between the, I say that now, but that's not the case. I was going to say there's a line driver that's sitting in between the inputs and what goes off to the adder, but that's not the case. I've got those in the wrong position. So let's try that again and make sure that I'm getting what I say I should be getting. And yes, I am still in reset. The key here is a voltage measurement. Yeah, I'm down at 0.6 of a volt here. Actually, I can measure probably right here. Yeah, 0.11 volt. That's certainly better than here where I'm measuring 1.42 volts. Okay, so my theory still holds. The inputs here are going through a line driver. The line driver is actually able to pull that signal properly low. My plan is to take a look at this and add in 74 HCT 541 line drivers here and here, and have those permanently tied so that they're always outputting, so that the change is literally propagated through. Now, these are LS logic, these are HCT logic. They are supposed to be compatible, so I will also look at replacing these two with HCT as well to make sure that those are working. Finally, coming off the fetch register, I have asserts out onto ALUB, and these are also LS logic, and I want to replace these with HCT logic so that I can properly drive both the LS and the HC logic in circuit. These are for the latch on the output, and I'm going to set those aside for now until we get voltage settled and under control. All right, that said, let me get these changes made. We'll come back, we'll give it a test and see where we landed. Okay, the fetch register assert onto ALUB and the ALUB line drivers on the ALU Adder both are very quick swaps. The ALUA line driver, just to condition those inputs, takes a little bit longer. Ultimately, I end up shorting power to ground for a short period of time. That creates a situation with the reset that takes a few power cycles to resolve. I'm not exactly sure what's going on with that, but I'll have to keep a close eye on it as we test. The first order of business here is to test the voltage input into the ALU Adder. So I'm expecting something a little bit higher than absolutely 0 volts. There we go, 0.007 volts, 7 millivolts. Looking at the B bit right next to it, 0.006 volts. So those are being pulled down nicely. Okay, now when I reset, nothing is asserting out onto ALUA or ALUB. Therefore, these are being pulled low properly by the 10,000 ohm resistors, meaning I'm adding 0 and 0, and the result is 0. Now, what I don't have is a proper latch up here that the 0 flag is coming on. Okay, that was an add of 0 to 0, which does indicate the 0 flag. So that is good. Let's see here. On reset, I want all the flags to be cleared, and they are clearing properly. So I'm going to call that acceptable for now, because there's no actual operation going on here. I just want to make sure that the LEDs are 0. I'm going to call that good at the moment. I'm still paying close attention to this voltage concern. Once it's, this is also a reset. So once things are in reset, when I power up, it's taking a little bit for that to settle down. I believe a lot of it is due to all the capacitors I have on the board that need to charge up. I have a feeling that my power on amperage is very high, and I am likely going to need some sort of a soft start mechanism, but that's not for today's video. Okay, before I get into dropping in my output latches here into this location, let me take a minute and talk about the signal shaping I need for that, because I need a latch signal and I need an output enable signal, and I struggled over those for a little bit of time. Okay, ignore the stuff up here in the corner. That was from a different thought process. I originally went down the path thinking I needed a latch in order to manage the actual latching of the ALU output and asserting that output out onto the bus. You can see I've got scribbles all over everything, trying to rethink as I go. Ultimately, what I realized was if I had two back-to-back addition operations, really two back-to-back ALU operations, I would have a signal that was high for the entire clock cycle, and then the next signal behind it would also be high for the entire clock cycle, meaning that I would never get the reset, meaning that I would never actually get the latch. That wouldn't work. Then I started looking at analog ways to address the problem, including RC circuits and then a diode with a capacitor, thinking I might end up having a signal that looked something like this down in the corner. But after thinking on it for a night or two, I finally realized I have everything I need up here off the top of the board where I actually shape the spike clock. I'm inverting the clock a number of times, about 12 times, and that then produces the delay that I need in order to get both the latch signal and the assert signal. It's just a matter of how big of a delay do I choose from. All right, so with that said, I should be able to now go and figure out how to replace these bits so that I get correct output. Getting into this, pretty much everything that touches, well, particular board here is going to have to change. So I need to put a line driver to drive the LEDs. I need a line driver to drive the what's effectively an ALU bus onto this latch, which is then going to drive out onto the main bus. And so all of this wiring is going to change. The pickups for calculating the Z flag, which are here, all need to come after that line driver, which is going to be whatever's on the ALU bus. So that's going to change as well. Okay, let's see if we can get into the changes here somewhat systematically so I don't make a complete mess of this. I want to put the latches up here, which is going to change where I pick up the main bus. So let's move that first. So that should be there, and that should be there. Okay, power, ground, decoupling. I tie together the signals I need for latch and output enable, and then I move over the inputs into the Z flag calculation. Okay, this takes care of the zero flag calculation. That's going to come directly off this ALU bus. The next thing is the inputs into the LEDs are going to be good, but the inputs into the line drivers need to be relocated up here onto the outputs from the ALU bus. I think I said outputs onto the ALU bus. The LEDs need to be driven by what's on the ALU bus, not based on the input from the ALU adder. Okay, two fundamental changes left. I need to tie the outputs of the line drivers up to the inputs to the latch. That basically establishes my ALU bus. The next thing to do is take all the adder outputs and wire those up to be into the line driver for, you know what? I've made a mistake. I've got LS logic still in here. I need to swap those out for HCT. Let me do that before I go any farther. Now that feels better. Like I said, the next step is to take the outputs off the ALU adder and redirect those over into the inputs of these line drivers over here so they can then be asserted out onto the ALU bus, which is represented by these blue lines up here. These are all going to have to be recut and reset. This was the fussiest bit of this entire process, as I had to keep track of the sequence of each signal and which actual breadboard connection it came out of so I could put it back in the right spot. The next order of business is going to be to connect up these signals and make sure that I'm handling them properly. There's going to be more than just the ALU adder, which is going to feed into this ALU bus. There's also going to be a shift unit and a logic unit that is going to be feeding into that as well. So with those three plus a do nothing, I need 4 signals that will handle that. But in keeping with the tenets of my design, I want to make sure that I demultiplex that actually here at the ALU rather than at the control logic. So I'm going to drop in a 74HC138 IC. And I'm going to use this to demultiplex the signal. Now I'll put a pin diagram up on the screen for you. I need one as well. And let's start with the A and B signal. These two signals are going to be the ones that select which of the different outputs are going to actually end up on this ALU bus up here. Now C, since I'm only using 2 bits to determine this, C is going to be pulled low. Let me move this over to the other side. And then I've got 3 enable signals that I've got to handle. One is an active high signal. That's going to be pin 6. 2 of them are active low signals. It's pin 5 and pin 4. Now the output signals are going to be 0, which is do nothing. Pin 1, which is going to drive the line driver up here. So this signal here needs to be relocated up here to plug into output 1. And then I've got output 2 and output 3. Both of those are going to be used to drive the other sections of the ALU, the logic unit and the shift unit. This signal is going to be repurposed to be my AND latch signal up here. I need another signal. Actually, I need several more signals if I start talking about the carry flag inputs, which we haven't talked about yet. Okay, I've got 6 here. I need to expand that wire to be 10 wide. Why 10? Because 6 isn't enough, and I don't want to do it again. Give me a minute to make a cable. Okay, here we go. First thing to do is to replace this over here. I'm just making sure that I've got things lined up exactly right over here. I am going to have to change the alignment over here. So my inversion bit gets moved over and my carry select. Okay, I made a pretty good mess of trying to move these signals around on the control logic boards. So I'm going to cut this here so you don't get the wrong sense of what I do, and I'm going to have to go through these one at a time and make sure they're all hooked up properly. The last thing to do now is to shape the signals that I need and bring them down here. Let me set up for that. All right, I'm going to put the list of signals up here in the corner, and let's start at the right-hand side and work our way to the left. The first signal down here is ALU latch. Now that's going to be the output latch up here. It's connected correctly here, but incorrectly here because, like I said, I made a mess of it. So I'm going to pull that signal. Well, I had a signal called ALU input latch, which no longer exists because I'm now latching the output. So I want to switch over to the control ROM code and make that change in the code. So instead of ALU input latch, this is going to be ALU output latch. Now that's tied to control ROM 8, and that is the least significant bit of control ROM 8. Control ROM 8 is here. The least significant bit is tied over here. And this one is NANDed with the spike clock. And that is no longer the signal I need in order to shape that. What I need is this signal to be ANDed with a delayed clock up here. And the problem is I don't have room to insert an AND gate on control ROM 8. So that signal location is out. But what I am able to do is drop in the NAND gates. Well, I'm making a mess of that. Drop in the NAND gates I need for the interrupt flags latches. And I happen to have these prepared. I think I had them placed in a previous video and I removed them. But I can add an AND gate at the end out here. And then this now becomes the place where I shape that signal. Now, 1, 2, 3, 4. So I can still pick up my signals here like I normally do. So this now means I need to spend a minute hooking this up. And then the signal I want to take is this clock signal. I'll be able to stick it in here. Now that'll be the least significant bit. So that's coming off of the latch here. That'll be the A input into that, where the result of that is actually going to come over here and be picked up by the least significant bit of my ribbon cable here. I have to build that ribbon cable. So, and while I'm at this, I will go ahead and build out all the rest of this to exactly match what I've got going on over here. I need to move that signal in the control ROM. Okay, remember that cable I reclaimed over here, 6 wide? Well, guess what just happens to fit here? And I have 2 signals here that are directly wired, pulled over here for carry select. And I'm going to drop in. So I'm going to drop in these 6 signals here, and then I can wrap these around. And I will bring them in. No, that's reserved. Let's drop them in here. Now, the least significant bit is my new signal here, and it is ANDed with a delayed clock all the way up here in my clock delay, calculating my spike clock circuit, but that's okay. There are 5 signals here left to be wired up. These are the interrupt context latches, similar to the 5 signals over here. And while I'm messing around in here, I think I'm going to go ahead and get those wired up, even though I have nothing that will use them yet. But as long as I'm messing in this area, I may as well mess completely. All right, let me work on that, get that settled. I'll rush through that real quick, and then we'll come back and make the connections down here so that I am now connected up. Have not programmed the EEPROM yet. Well, most of this is a duplicate of what I've already done with Control ROM 2 and 3 and 4 and 8. So I'm going to skip ahead on this and get to some more important pieces. Okay, and the final connection is to hook up the actual latch. Next in line is the invert, which I've got tied low. The next 2 in line are carry select, the 2 bits associated with that. I've already got those wired up, so I don't need to worry about that. The next 2 are going to be the select that is used over here on this end to select what is actually asserting out onto the ALU bus up here in blue. Right now I'm going, since I have nothing else, I'm going to tie that to 0, 1, and 0, 1 should be, or is, output 1 here. So let me get that tied quickly. And the next 2 are going to be the selection for which carry flag actually carries up into the flags. And again, those are not hooked up. I don't have a selection for that now, so I'm going to tie those low as well. And I will come back in the future and clean that up. I have 1 additional line I have to draw, and that's this one down here. And that one, I believe, I'm just going to route it around here rather than getting a single ribbon cable. So let me do that. Okay, long wire, but it's settled. Okay, I did manage to forget 1 signal, and that is for the ALU result latch, its output enable. And this would be asserting out onto the main bus, so that's going to come from up here in the main bus asserts. Now, I changed this to be the main ALU adder, but in reality, I need that just to be the ALU result. And let me just call it result. Now that is going to be on IC3, and it is going to be the most significant bit on IC3. So coming back here, IC 0, 1, 2, and 3, the most significant bit here. So that's going to be the red one here. And so that's going to be there tied to one of these unused bits down here, the next one in line. I got to clean that up. But then over here, I now need to drag that. Let's see if I can make this work. I need to drag this signal up here to that output enable. Now my desk is a complete disaster right now. A lot has happened. I need to straighten stuff up, and I need to get a decoupling cap on here. Just generally review what I need to address, and I think we're going to be good to test. Cross your fingers. Okay, I've got the build out, it's powered up, and I'm ready to test. Now, I've run through a preliminary test on my own, and that was before I put the cameras on, and I know it's not perfect, so there are some things to troubleshoot. And where this goes from here is going to depend largely on how big of a problem I discover. Now, I am afraid, I'm concerned, that the problem may not be easily overcome. Let me explain. I've got some messiness in the clock that I still am not happy with. In other words, I've got 12 inverters in there that is delaying a clock signal to the point where I'm trying to get a spike out of the clock so that I can do some things in kind of an intermediate state. And the faster that I run this clock, the less time I'm going to have for that state to settle before the next clock cycle or the next clock event takes place. Now, I made a tactical error in the build here, and if I was to do it all over again, I would have started with the ALU. It is by far the most complicated thing in this build, and a lot of things are dependent on how that operates, and I would have, hindsight being 2020, I would have started with the ALU and built that out fully before I started putting any of the other things around that. So there is an opportunity there, and honestly, if you're looking at doing something like this on your own, I would recommend starting with the ALU, possibly even before the clock. There's a lot going on that has to be taken into account, and I have done myself a disservice by bringing it in as one of the middle items as opposed to one of the first items. All right, so that said, what I think I'm going to discover here as I go through this, I know I have a timing problem. I believe that the solution to the timing problem is only going to make my situation worse and make this build more fragile than it should be. I need something that is robust. Well, I don't need, but I intend to build something that is robust and solid and can be run at many different clock speeds with far greater stability than what I've got right now. Now, I'm going to make the effort to solve this within the constraints of what I've got right now. But if I have to augment or change the clock any more than I already have, then I'm going to take a step back from this build. We'll extract the ALU out, I'll build a new clock, and we'll go down the path that I should have done to begin with. And that will be to stabilize the ALU and complete its build, and then insert these components back in around it. So that said, I'm going to start testing my way through this. I'll have to get the oscilloscope out. I know that for a fact at this point. And we'll have to start looking at signals to make sure that things are happening in the right sequence. So let me get that prepped for you. I've got the scope out, and I'm not hooked up yet. I need to decide which signals exactly I want to start looking at here. So let's start walking our way through the code. Reset. So this is a move of the 0 register, which is a pseudo register, into R1. That forces R1 to be 0. This is a move of the same RZ0 pseudo register into R2, which is going to force this to be a 0. Finally, this is an add of R1 to R2, storing the result back in R1 to ensure that the ALU is prepped at 0. And that has worked. It has not always. This is a clear carry. I'm sorry, set carry, not clear carry. So that takes care of setting that particular flag up here. That's the second flag in. This is a move of this immediate value into R1, which works. Forces a no op up here. This is a move of this immediate value into R2. Now these are alternating bit patterns such that when I add them together, I end up with all the bits set. And that's what I should see over here. This force to no op up here, this is my add instruction. That add looks to have worked properly. But when I go to latch that into R1, 0 came across, not all F's or all 1s in binary. That also changed the inputs here, which should be completely disabled. So something is still being asserted out onto ALU A or ALU B. I'm not exactly sure where that is. Let's start with that because that is a concrete problem at the moment. So I will power this off and disconnect power on it because that's part of the problem I have with that. And let's figure out exactly what is driving that LED high. On the line driver that is driving that signal, it is outputting high, which means that I get high coming in. Tracing that backwards, that means I've got a 1 on the ALU bus, internal bus, which means that I'm adding to have a value of 1 for the least significant bit. Now I've got to pull up the pin diagram for the full adder here, and I'll stick a copy of this up on the screen for you as well. I've got inputs A up on the top here, inputs for 1 up on the top here. Now these are going to be, what did I do? Okay, so that's correct. So that is sum 1, which is low, high and low should equal 1 unless carry 0 is coming in high, and it is coming in high. So that then is what is driving that. I need to trace my carry select backwards. Carry select is, they're both high. These are coming off of here, high and high. So my carry select is high for a no op instruction. Okay, that leads me back to the programming of these things, these EPROMs. So which one is suspect? Carry select is on control ROM 9, that's over here. So this is one of my replacement EPROMs. So let's dump the contents of that. And that is properly 00 on there. Not what I was expecting to see. So that means I need to trace this back now and make sure that I'm getting the correct output. So let me pull this, drop this back in place. That looks like it's providing the correct value now, 0 and 0. And I did not reprogram that. All right, so let's try this again. Forcing zeros, add the two zeros together. Carry should be 0 or not set. 0 is set, which is proper. Move the value in here, move the value in here. It's taking a little bit longer for that particular light to come lit, but I'm not exactly sure why. My 0 is set. This value is changed. It should not have latched to 0. It should have latched empty for 0. But I still have zeros here, but I don't have the 1 here anymore. That instills a lot of confidence, doesn't it? What I need to do is I need to get a look at the latch signal, and I need to compare that with the output enable signal. Let's go with single shot here. Let me reset. Step, step, step. This should trigger both of those, and it did not, but this one is for some reason. So why is set carry triggering the outputs? Okay, I found it. Can you see it? I'm shifting the wrong number of positions. Copy and paste problem. All right, let me reprogram all the EEPROMs again, and we'll give it another shot. Here's the next problem. This instruction is to load this value into R1 and then pass on a no-op, which it does successfully. This instruction is supposed to load this value into R2 and pass on a no-op up here, which it does successfully, sometimes. That same instruction passed on a load operation, which is to load this value into R1, which it did successfully. But it incorrectly passed on a 1 up here. Now, why? If you look carefully here, I was playing around with the resistors associated with the least significant nibble on the instruction bus. I call that loosely because there's only two things tied to it, but out of the fetch register asserting onto the instruction register. And I had 4 resistors in here at one point and managed to remove one somehow. Not exactly sure how I did that. And so now I've got a floating line going into the instruction register. These are 2 mega ohm resistors. These are still 1K ohm resistors down here. But if I stick a 10K ohm resistor right there next to it, notice even though I'm going fast, I am actually properly pushing the no-op up. And that's proper. So with that, I'm going to have to pull all this out and replace all of these 1K pull downs and this mishmash over here with 10K pull downs. I was hoping to not have to do that, but it looks like I don't have a choice. Well, I do have a choice, but I'm not going to take the choice at this point. I'm going to go ahead and get that done, make sure that I'm stable as I possibly can be. I'm not going to make you sit through that. I'll be right back after I get that done. I managed to replace these resistors with 10,000 ohm resistors. These are the pull downs associated with the instruction, which is what forces the no-op up here. And while I was at it, I went ahead and took care of the main bus. These pull downs are used on the main bus as the RZ pseudo register. So, okay, let's take a look now and see where we landed. So once again, moving 0 into R1, moving 0 into R2, adding the two together and storing the result back in R1. And that works because the contents of R1 and the output are the same. So I believe that's just overcoming the timing concern. Set carry, that's going to be this next LED that's not on. Now it is. Now I'm moving this value into R1, forces a no-op up properly. I'm moving this value into R2, and again properly forces a no-op up there. Now I've got my add taking place. When I push down on the clock, I am expecting this value to latch in R1, and I'm getting a 0 that's latching there. So I do still have a timing problem related to the ALU and what's latching, and then my contents here have changed to be that of R2, and that's because I'm still pushing R1 out onto the bus. Okay, so I still have now a timing problem with asserting out onto the main bus and my load, which is happening here, and trying to determine if I've got those in the right sequence. Now, my concern is I've really actually developed a 4-cycles clock without actually properly developing a 4-cycle clock. Okay, I'm going to pull this out of the way here for a moment, and I'm going to explain what I believe I'm going to find the problem to be, and I'm going to do that on paper. And then I'm going to pull the build back out after that and see if I can demonstrate to myself that I've actually properly predicted what the problem is. Give me a minute to make some room for some paper. Okay, we're going to get into a little bit more details about the problems that I was talking about 13 minutes ago. And this is a bit of a history lesson for the build. And bear with me as I go through this because it's going to be extremely relevant in the future, I think. So the actual clock itself has a signal which looks like this. And the clock cycle is basically between the 2 dotted lines there. Now, there is a transition that happens here at A, and I have the same transition basically at the end of the clock cycle. And then B is the transition that happens in the middle. That's the falling edge of the clock. Now, I've got an inverted clock, and I recognize that. And I recognize that the clock cycle really doesn't end after this rising edge and start before this rising edge, but it really is the rising edge itself that delimits this. But for the sake of the illustration, I've drawn it like this, so please bear with me as I go through this. I have from event A to event A, so along the entire cycle of that, I've got all my bus asserts. At event A, I'm also doing my instruction latch. That's at the fetch register as well as the instruction register. At event A, I've also got my control word latch. And that is on the control ROMs. Those are the latches of the data coming off the EEPROMs. at event B, this falling edge, is where I am performing my AND latch. And that worked for me pretty darn good until I started having problems with jumps and loads and the like. And I ended up adding in there this signal, and I'm drawing it a little bit below, but it really is right over the top. It looks something like this. Okay, and that was what I'm calling the spike clock, or spiked clock. And this rising edge here is transition C, and the falling edge back down here is transition D. So what I ended up doing is at D, I added my register load, increment, decrement signal. Now, again, I've shaped it differently. I'm not getting into the inversion and everything else that takes place. And finally, I got into the ALU, and I have now added what looks like a delayed clock, where I now have transitions E and F, which have been added. So the ALU now has the flags latch also happening at B. I have at C, this rising edge transition here, I've got the ALU result latch. And from E to F, I've got my result assert. So that is during this period of time, so that it happens theoretically prior to the load of the register and is available up into the latch, past the latch actually. So where do I think the problem is? Well, I believe it's in this section here, where I've got all of these transitions piled up that I'm trying to orchestrate into a specific sequence. They're certainly not happening in the sequence that I expect them to happen, and I may have incorrectly identified what sequence they should be happening in, meaning I don't know what's going on. I honestly believe that D and C and the E through F assert, those are my critical measurement points. And I need to make sure that all three of those signals are actually happening all in the correct sequence, so that at the end of all of that, I end up having a result that gets added and then latched and then asserted out onto the main bus and then loaded off the main bus in the correct sequence. My prediction is that the load, increment, and decrement at the register is happening before I'm actually asserting the result out onto the bus. And that's what I need to start measuring. Now I've got C in there as well. I want to make sure that I'm actually latching at the correct time, that I am doing the result assert, and make sure that all of that is happening sequentially properly. So I'll grab the build again, pull it back out, zoom back out, get myself set up, and grab the oscilloscope, and let's see if we can measure this sequence and make sure that things are happening in the right order. All right, I'm set up such that the yellow trace is measuring the clock, and I'm going to compare that with the, actually I'm going to compare that with the output enable. I want to confirm that that is really the signal that I'm expecting there. So that should, as I corrected in the previous segment, that really should be A to A here. Let's see how right I am, or how wrong I am for that matter. Okay, that should be A. So that's low. When that falls low, I need that on the rising edge. That's not the signal I wanted to measure though. It's the one after the second add, so I'm loading the registers for that. That looks reasonably good. Now let's take a look at when that latch happens. So that's latching way early. All right, let's trace that signal. That's control ROM 9, and that is the least significant bit on there. All right, control ROM 9, the least significant bit is this one. That is NANDed with this clock, which probably should be an inverted version, so I'm going to move it over 1. Let's try that again. Yeah, That's the problem I'm having. So now that it's inverted, it's latching at half clock cycle. So let me go back as far out as I can. So this is now connected at the very end of the chain of delays here that's used for the load. What I need to do is I need to compare against the R1 load. Now I want my trigger to be on the, no, I need the shaped signal. So I actually need over here, that should be bit 1. So I need to trigger on the falling edge of that, which is correct. So this is the load. The load completes somewhere about in this space. This is the latch. And that latch needs to complete before the load. There's not enough time for the propagation delay to take place. This is indicative of the problem that I'm having. Here I am inserting yet another 6 inverters into the circuit just to see if I can create the right amount of delay. Okay, let's see what that does. So I've now got 18 inverters in there, 19 if you include this one here. 19 inverters in there, trying to delay that signal enough. And that did not work. See if I can delay that latch a little bit more. So that has not changed the behavior nearly enough. Okay, let me come back over here with this. So that's the latch, that's output enable. So the question is now, what's on the main bus? 0, 0, 0, 0. So I did not latch. So that is working properly there. I did not latch a good value. Okay, so my latch is happening too early. Can I correct that? I think I need to be on this one. All right, let's see what's on the main bus now. That worked. That is a damn mess. I now have 18 inverters in there in order to delay my signal properly to get this to work. Okay, I've got one bad signal over here somewhere that's not adding properly. All right, well, I added, but it ain't working right. Let me clean up my test equipment here, and then I'm going to have to look at all of these signals to find out why there's one that's taking so long to actually process. Okay, before I go and take anything away from this, I figure it's probably better to spend a minute and make sure that I've got all of my signals sequenced properly. So the first thing is I want to take the clock and compare that to the latch. So I need to be triggering on channel 1, and I want the rising edge of the clock. So the clock is the yellow and the latch is the blue. And that looks like about 100 nanosecond delay. So that at least it should be in the correct sequence. Okay, now I want to take and compare the latch against the output enable. I'm really not too concerned with that, other than I want to make sure that output enable is not going away before the latch gives up. So the blue trace is output enable, and it is going low before the latch itself. So theoretically, I am outputting the old value, and then I'm latching and outputting then the new value after that. So that should theoretically be good. Okay, that updated. So I have latched. I should be outputting onto the main bus. I can check this down here. And I'm not getting everything I was expecting. So my least significant bits are outputting the low value, my most significant bits are not. So I have 7 bits high and 9 bits low. So could this be the problem, or one of the problems, that I need to move that latch to be ahead of the output enable? Now I believe the output enable is strictly based off of the demultiplexers up here in the corner. Or am I latching too quickly? Maybe I'm latching too quickly. I had added another set of inverters off camera just to see if it would work better. So let me go back to what I had been testing previously. And so that brings those two much closer in line. But still that same bit that takes a while. All right, I'm going to ignore that bit for the moment. I am now loading and latching, in air quotes, the correct thing. So let's do that again. Yeah, that's worked. All right. So now I need to compare my latch against my R1 load. R1 load is control ROM 3 bit 1, and that is the shaped signal. Now I want to trigger off of channel 2 the rising edge, because that's when the latch is taking place. So let's see what that does. And it's almost like I still need to shift that spike clock to be later, because if the load ends about here and my latch takes place just about, or the latch takes place about there, I need to shift that spike clock to the right a little bit. So I do then need to add an additional delay in here. So now I've managed to bring the latch forward. The question now is do I have enough of a delay here? I don't need to change that. So the question is am I outputting the correct stuff? I am not outputting the correct stuff. Let's try an absolutely obscene amount of delay here and see if I can't get this working properly. Okay, here are 18 more inverters. Yeah, I said obscene. So 24 and 18, the 42 inverters that I would have in here built into this delay. And I'm going to take a few minutes here and get these wired up. And this is going to be not the best wire job I've ever done in my life, but the point here is to perform a test. This is not going to persist for very long. An absolutely ludicrous number of inverters for a delay. You can see now that my load is happening well after my latch on the output. That is now working the way I believe it should, with the exception of my 4-bit. Okay, well, I think I've got everything worked out here. I know the video is well over an hour at this point. I'm going to go ahead and stop here. I had hoped to get through all of the testing as well, but I'm going to save that for the next video. So I will address that lazy bit that just won't seem to change quickly enough and get that taken care of. We'll go through all of the tests associated with the ALU Adder. And then I'm going to start looking at the clock a little bit. I am not pleased with that situation at all. I have effectively developed a 4-cycle clock or 4-state clock without actually properly developing a 4-state clock. So I'm going to take a step back and look at that and see what it takes to get that done as well. That will span over several videos. as I continue to try to move this forward, but ultimately I'm going to have to revisit the clock yet again to make sure that I'm getting good clock signals going here. Coming up shortly is going to be memory as well. I need to get RAM memory in there. I still have 3 additional general purpose registers I need to add, so there's plenty to do here still. And then I've got to start looking at ways to reduce the size of this footprint so that I can get more of it in camera view. So I will be looking to convert a lot of this to PCB shortly. This has been a fight. I'm glad we've gotten at least to this point. We'll see you soon.